So that's the main consequence in that case. Okay. So what can we do with this? Well, one thing is we can create bounds on U, okay, using the max principle, as in the following theorem. So again, let's suppose that we have a harmonic function on some omega, and that U is equal to g of x on the boundary, right? So we have a nice boundary value problem for Laplace's equation. Let's say that G is continuous, okay? And we have that U is satisfies the properties that we wrote down for the maximum principle, okay? Well, if omega is connected, okay, and G is greater than or equal to 0, so it's non-negative for all x that live in d omega. And we also have that G is greater than 0 for some x in d omega. Then we can say the following thing, that U is strictly greater than 0 for any x in omega, okay? So using the weak and the strong maximum principles, we can put them together to prove this theorem. It doesn't take too much work. So what do we have here? We have, we have some function. So imagine you have some boundary here, right? This is omega, this is d omega, and we kind of unroll the boundary here, right? So this is d omega, and then G, I don't know, looks something like this, right? So here's our G as a function of x in omega, right? So this is me unraveling that, right, in 2D, let's say. The strong maximum principle says that everything on the interior, or I guess it'd be the strong minimum principle, needs to be bigger than the minimum of G, right, which would pull us away from 0 on the interior. And then, of course, the maximum on the interior can't be any bigger than this max here, okay? So essentially, the weak maximum principle implies that the minimum principle implies that the minimum over the closure of omega of U is equal to the minimum on the boundary of G. The strong version of the minimum principle gives us that U is strictly greater than the minimum of G for any x that lives in the interior of omega, okay? Otherwise, okay, U is constant, right? But we know that U can't be constant because we have we have continuity, and we also have values on the boundary that are non-zero, okay? So since U not constant, since G is not constant, okay, U is then strictly greater than 0, okay, on omega, okay? All right, so that's one thing that you can do with minimum principles. I mean, not surprisingly, and maximum principles is that you can bound functions. You can sort of string results like this together in order to get bounds on solutions to boundary value problems. And as you'd expect, you can also use the maximum principle to prove uniqueness, okay, as we did in the case of the heat equation. So the last thing I'll talk about before I move on is uniqueness proof. It's actually not very involved. It's shorter than energy method type proofs. There is an energy method type proof for Laplace's equation. We'll show it here using the maximum principle. Okay. So uniqueness. How do we prove it? Well, let's say we take not just Laplace's equation, but Poisson's equation, right? So remember, usually in uniqueness proofs, we get back homogeneous equations and then we deal with those, right? So it can have some, I guess, inhomogeneity here in the actual PD, and you can have inhomogeneous boundary conditions. We're gonna make a couple of assumptions about F and G, just that they're continuous. That's all we need. And I'm gonna call this equation star. And so our uniqueness theorem states that there is at most one solution, U in C2 omega C over the closure of omega of our boundary value problem, right? I haven't proved its existence, so I can't say that there's exactly one, but I can say that there can't be more than one, okay? How do we proceed with this proof? Well, the same way that we have in the past. Essentially, we let U1 and U2 both be solutions, okay? What do we do now, right? Well, we can make boundary value problems for the difference of these, okay? So if we take V is equal to U2 minus U1, and W is equal to U1 minus U2, okay? Then we have that minus Laplacian of V equals 0, okay, on omega, and V equals 0 on the boundary, minus Laplacian of W equals 0 on omega, W equals 0 on the boundary, okay? And we don't even need the strong maximum principle. We can just use the weak maximum principle, okay? V is bounded from above by 0, and W is bounded from above by 0. You could also just use the max and minimum principle on either V or W. That would work fine too. But what this means is that U1 minus U2 is squeezed between 0, which implies that U1 minus U2 is equivalently 0, or U1 is strictly equal to U2. Okay, so we don't have to go through this process of dealing with functionals and things like that. We do have this assumption that we need of twice continuity, just because we need to be able to plug this into the PDE. But essentially squeezing the different solutions in this way, we can get the uniqueness result. Okay. Any questions before we jump to the next topic? Okay. All right. So we're gonna go through a separation of variables calculation now for Laplace's equation. this is actually going to kind of build up nicely to the topic of Green's functions, because the solution that we're going to get at the end is going to it's going to involve a convolution, and that convolution is going to involve a Green's function. So, or at least, yeah, I think in some cases it's convolution, and others, yeah, it might just be an integral. Okay. So, so Green's functions are they're sort of like fundamental solutions, except they work on boundary value problems. And so this is a nice